Alright, here we go. Optimization problems, second day. So let's just jump into these examples. So go ahead and pause that, write down the example, and then I'll go over it. So again, remember, we need to find a primary equation and then secondary equations. But I'm going to start this off by drawing a little picture of what it is that I'm actually looking at. So first of all, I have a rectangular piece of paper. Rectangular piece of paper. And all I know about this paper is that, first of all, here in the middle, there's going to be 24 square inches of writing. I also know that the margins at the top and the bottom of the page are 1.5 inches. So, oops. Let me back that up. There we go. So 1.5 at the top and the bottom. And I also know that at the sides it's going to be 1 inch margin. So we want to know what the dimensions of the paper to be so that we use the least amount of paper. So this means that we're looking for a minimum. We're trying to find out what the least amount of paper would be to get this. Now, we need some variables for these sides. You can use any variables you want. When I did this, I used length and width. So I said that area, that area of the inside is length times width. And we know that that area was 24. And then I jumped, so this is secondary, right? Because the primary equation, oops, I forgot an A. The secondary equation is talking about that middle. That's going to have something that we plug in there. But our primary equation, the one that's going to answer this question, is actually the same equation, right? It's the same formula because we're looking for the area, but now we're looking for the area of the big piece of paper. So I'm still going to use, maybe I should change this, and since this is the smaller section, I'll use small variables in here. So length times width, length times width. All right, so when we're finding the area of the overall big piece of paper, right, this, I'll outline it in green, like this piece right here, we're going to use the information that we know and plug that in. So first of all, the area is, if we look at the overall length, I should have changed these L's and W's inside here too. So if we're changing that, I'm sorry, let me just change this real fast. This is my length and my width. So if we're trying to find this overall paper, this would be our big L, big W right here. So the overall length would be little l, so little l, plus the two sides, 1 plus 1 would be 2. And then times the width, it's hard to tell the difference between a capital and lowercase w when you're doing this, but anyway, the width, we'll call that the height, basically, is going to be w, and then 1.5 plus 1.5 would be 3, so plus 3. So this is where we are going to use our secondary equation because we need this to be one variable. And right now we have two variables. That's not okay. We need one variable. So we're going to solve this for a variable. Take your pick, L or W, whichever you want to use. I'm going to solve this for L, so I don't have to keep writing those cursive L's like I did there. So L is equal to 24 over W. So I'm going to plug that in. And honestly, that's the only reason why I'm doing that, is so I, for whatever reason, decided writing cursive L's, and I don't want to do that anymore. So I'm gonna change that. I'm gonna solve that for L, so I can plug it in and just use W's. Okay. So this is what I'm looking at. So all I'm going to do from here is I'm going to simplify this by just multiplying it all out, and then take the derivative and set it equal to 0. So if you want to pause the video and try that and then come back and see if you have the correct answer, I would encourage you to do that just to see how you're doing with these problems. So that's what I'm going to start with. So If you want to pause the video, go ahead and do that. I'm just going to multiply all this stuff out, combine like terms, take the derivative, set it equal to 0. So go ahead and do that. So I end up getting 30 plus 72 over W plus 2W. So that's the formula for my area. Okay, if you remember, hopefully you remember, it wasn't that long ago, hopefully you remember, the whole process of finding a minimum, which is what we're looking for, the least amount means we're looking for a minimum, is to take the derivative and set it equal to 0. So the derivative of 30 is 0. The derivative of 72 over W, you can write that as 72 times W to the negative first. However you want to do that, you get negative 72. I'm going to write it like this for solving purposes here in the next step. Plus the derivative of 2W would be 2. Okay, and when we're doing these, don't think of it in terms of like related rates or whatever, where we think, well, is it in terms of, are we doing the derivative with respect to x or y or t or what is it? These derivatives, because we chose the variable, we're taking those with respect to whatever variable we chose. Okay, so all right, now we're going to take this negative 72 over w squared plus 2, and we're going to set that equal to 0. Okay, so subtract 2, multiply by w squared, divide by negative 2, and take your square root. Now, we would have a plus or minus here, but we're talking about a width, so we can't really have a width of negative 6 inches. So, like I said, even though we could have the plus or minus when we do a square root, we're going to ignore the negative because there's no such thing as a negative length. So our width is 6. So now, if we know the width was 6, that means that the length, little l, length, has to be 4, right? Because length times width gave us 24. So we know that if we found the width to be 6, that means the length has to be 4. So we know those parts of that paper, but that does not answer the question, because that is just the pieces that are, I'm sorry, that's the part of the paper that the writing is on. We want to know the overall dimensions of the paper that would give us the least amount, using the least amount of paper overall. So we're going to come back up here, take our L and add 2 to that number to get the length, because there's an inch on one side and an inch on the other side. So L was 4, so that's going to be a 6 inch by, what's the height? Well, that was the width we found out to be 6, plus 1.5 plus 1.5 would be 9. So a 6 inch by 9 inch piece of paper would be the one to use the least amount of paper and still be able to fit 24 square inches of print with the margins that we were given. Okay, so there's one. Next problem. Which points on the graph of, well, if I see graph, I'm going to draw a little sketch so I know what I'm looking at. I'll draw a little better sketch than that one. All right, so start with my coordinate plane here. 4 minus x squared. So this means parabola, negative x squared flipped upside down, with the plus 4 means it's moved up 4 units. Okay, so I have something that looks like this. Okay, and we want to know which point on, or which points on this graph are the closest to this point here at 0, 2. So now we know that this point here at 0 is 2 units away, right? If we go straight up to that vertex, that's 2 units away. But is there a point somewhere else on here, you know, somewhere on this graph, that would give us a smaller distance, right? Because we want to know the closest. So that's what we're trying to see. Now, because this is symmetrical here, the only time we would have one answer would be if it is the vertex, okay? Other than that, if there's a point, let's say for example, if this point right here is closest, there's also going to be one on this side that's symmetrical because it's a mirror image around the y-axis. There's also going to be one on that side. Okay, so that's something to think about as well. So closest, again, like I just said, closest means we're going to use distance. So hopefully you remember your distance formula. If not, it is x minus x1 quantity squared plus y minus y1 quantity squared, which is really just the coordinate plane form of your Pythagorean theorem. I don't know if you were ever told that before, but that's basically all the distance formula is. So we're going to plug stuff in here. Now, 0, 2 is our x1, y1. Okay? When we're plugging this in, remember we need one variable to be left. Okay? The easiest one here is, it's easier to be left with x. And you might be thinking, well, what do I do with y? How do I know what y is equal to? Well, right here, we're given that in the problem that y is 4 minus x squared. So remember, your primary equation, this equation right here is your primary equation, helps you answer the question. The question is, which points are closest? So that's asking you the distance. Your secondary equation is what is being plugged in. So, that's what is plugged in to help give you the same variable. So we're all left with like just x's or just y's. Okay, now if we tried to solve this for x and plug it in here, you could do that, but you would have scenarios because you would have x equals, the plus or minus square root of y minus 4, or backwards 4 minus y, and that's just not very easy. This is already solved for y, so we can plug that in. So let's go ahead and do that and simplify. So square root of x, we're just going to leave as x minus x1 was 0 plus y, we'll use 4 minus x squared minus y1 is 2. Quantity squared, and that is all underneath our square root. Okay, now from here, we have a couple steps of algebra to do before we take our derivative. But again, just like in the last one, if you want to pause this and try to finish it out on your own, and then just check back in, watch the video, and see if you get it correct, I would encourage you to do that. So go ahead and pause it, try it, and then come back. Okay, so hopefully you tried it and you're coming back to check your answers. But if not, follow with me and I'll go over the whole thing right now. So x minus 0 quantity squared is just x squared. If I'm squaring this, first of all, 4 minus 2 is just 2 minus x squared quantity squared. So instead of rewriting that whole thing, I'm just going to make a little note there underneath it. So when we square this, 2 squared is 4, minus, multiply these 2x and then double it, so 4x squared, plus the last one squared, x to the 4th. Clean it up. X to the 4th minus 3x squared plus 4. All right, there is your distance formula. Now we're ready to take the derivative and set it equal to 0. So the derivative, I'm going to slide this over here. The derivative, d prime. Remember, when we take the derivative of a square root, hopefully you've recognized the pattern by now. It's always 1 over 2 times that square root and then multiply that by the derivative of the inside, which would be 4x cubed. This is chain rule, minus 6x. Okay, now we have to set this equal to 0, which just means we need to know where is this equal to 0. Because that's where a function is, a fraction is equal to 0 is just where the numerator is equal to 0. So 2x, oops, still got another 2 in there. 2x squared minus 3 equals 0. So where is this 0? Well, 2x is 0 when x is 0. And 2x squared minus 3 is 0. Set it equal to 0, move the 3, add 3, divide by 2. You get plus or minus the square root of 3 over 2. Okay? Which you could rewrite that square root of 6 over 2 if you wanted. But again, like I said, it's not necessary to do that. All right, so now this one is a little different than the other ones because the ones we did in the previous notes, the 371 notes, and the first problem we did here, that just gave us one answer that made sense. Like, you know, we ended up when we did this, we would have gotten a positive or a -6, but the -6 didn't make sense because we can't have paper of -6 length or -6 width. So over here, though, we have some points that now we have to check. So by the first derivative rule, or the first derivative test, we need to check all of these. All right, so let's plug in our values. We have 3 numbers that we need to check and also some values around them. So I'm going to make kind of a bigger table here. I have negative square root of 3 over 2. I need a number less than that. So let's go make sure we're definitely less. So negative square root of 5. Negative square root of 3 over 2. And then you may need to, if you're not sure exactly where square root of 3 over 2 is, you may need to, like, you know, just check that and see. When I did this, I just used 0.1. Negative square root of 3 over 2 is a little bit bigger than 1, or -1, I guess. So you could use -1. I knew that I needed to use a value between there and 0. And so when I did this, I just used -0.1 because I knew that was between there. But again, you could use your calculator to figure out that this is a little bit bigger than 1 or -1. I guess smaller than -1. And then you could have used 0.5 or whatever. But anyway, like I said, I just used 0.1 and -0.1. And then square root of 3 over 2, and then something bigger than that, I used 5. And we are looking at the first derivative. Remember, we are trying to find the closest, so we're looking for a min. And if you remember, a minimum, when we're looking for a min, this means it's going to go from a negative to a positive, right? Negative to positive, because it's going to go like this. A negative slope to a positive slope. Okay, so that's what we're looking for here. So we know this gave us a 0, this gave us a 0, and this gave us a 0. So let's plug in our values into, and again, we only have to check in the numerator because the denominator has to be positive. So we're just going to check the numerator and see. Okay, so let's plug that in here and see what we get. So -5. If we plug -5 in here, what do we get? Well, negative times positive, which means this would be a negative. And we plug in -0.1, so that would be a negative right here, and also a negative on the inside, so that is a positive. So right now we know that this is a min. 0.1 gives us a positive times a negative, which is a negative. 0 would be a max, so we're going to ignore that one because that's not what we're worried about. And when we plug in 5, we get a positive times a positive, which is positive. So these two are both mins, plus or minus square root of 3 over 2. Okay, now let's come back up here because it says which points. It doesn't say which x values, it says which points. So we are not done. We need to take those x values, so negative square root of 3 over 2, and we have to plug that into the original function, the 4 minus x squared. Okay, so plug that into your calculator. 4 minus, which our x is negative square root of 3 over 2, so when we square that, we just get 3 over 2. So 4 minus 3 over 2. If we want to leave that, you get 2.5, but if we want to leave that as a fraction, oops, quit. 2.5 as a fraction would be 5 over 2. So that's just going to be 5 over 2. Okay? Now, like I said before, since we know that this is a symmetrical function, we know that both of those y values will be the same. They're at the same x values there because of this function. So negative square root of 3 over 2 5/2 and positive square root of 3 over 2 5/2 will be your answer for that one. Okay, so again, there's 2 more examples of optimization problems. Here are some more problems for you to try. Page 220. Again, I tried to give you most odd problems, but there's a couple of evens in there. And again, like I said before, if you have any questions, please let me know, and I will get back to you. So I'll send out another video for next week, finishing up optimization, and also giving you some practice worksheets. So that's all we'll be doing next week. Is I'll send you another optimization video, and then I'll send out, I think I have 3 worksheets that will basically take us through the rest of the week. Still looking at having the test on, I was thinking next week, but I'm going to push that back now, so that the test will now be, I'm thinking like the 17th. Okay, so that's the plans for right now. So if you have any questions, just let me know. Otherwise, you guys can go ahead and work on these problems, and yeah, just let me know if you have any questions.